Welcome back everyone, Houston Math Prep here. Remember in our previous video we defined the derivative of a function f prime of x, the derivative of some function f of x, and that was the formula for the slope of a tangent line anywhere on the original function f of x. We gave you this definition last time at the end of our previous video. The limit as h approaches 0 of this difference quotient here, f of x plus h minus f of x over h. What we're going to do in this video is just practice finding a few derivatives using this limit definition for the derivative. All right, so we've got our definition up here in the corner. We want to use this limit definition of the derivative to find f prime of x for the given function here. This function is 3x minus 2. So we'll go ahead and first write down our definition for the derivative in terms of this function. So we have the limit as h approaches 0. So we'll say limit as h approaches 0. Now you'll notice the first thing in our definition is f of x plus h. So what I need to do is, that's saying put in x plus h everywhere you have an x in your f of x. So f of x plus h is going to be 3 times, now x becomes x plus h, so 3 times x plus h minus 2, right? That's our f of x plus h minus f of x. Now that's just the original function itself. So minus 3x minus 2. And then all of that is going to be over h, and we'll take the limit as h approaches 0 of this. Now let's do some simplifying on the top here for sure. So we'll have the limit as h approaches 0. We don't want to forget that that's part of what we have. Let's distribute everything that we've got. So we've got a 3x on top plus 3h minus 2. And then don't forget to distribute your minus here. So we have a minus 3x. And then we have plus 2. So that's our top there over the bottom. We just have h. So you notice some things that reduce, right? You'll notice we have 3x and we have minus 3x. So those will reduce to 0. We have minus 2 and we have plus 2. And so those will also reduce to 0. So you can see that we get the limit as h approaches 0 of just 3h over h. Now what you might notice is, well, if I take the limit now as h approaches 0, I get 0 over 0. Yes, that's true, but we can still do some reducing before we need to worry about doing any sort of limit, right? So if we have 3h over h, that's simply going to reduce to 3, right? So we'll have the limit as h approaches 0 of 3, and that's our most simplified version of our difference quotient. Now, the thing with this limit as h approaches 0, there's no h really even left in this statement. So to say, well, what do we get when h approaches 0, this statement is not really needed, right? It's superfluous. There is no h to even decide what would happen as h approaches 0. So really our answer for this one is just 3. So the derivative f prime of x, when we have the function 3x minus 2, its derivative is just 3. Looking at another example, our f of x is now square root x. We're going to use our limit definition to find the derivative there. So f prime of x is going to equal the limit as h approaches 0. F of x plus h, so that says, again, remember, plug in x plus h everywhere there's an x. So inside of my root, I'll have an x plus h now. So that's my f of x plus h part. Now minus f of x, so minus f of x is just the original thing, so minus square root x. And we'll take care of that. And then everything is going to be over h, and we'll look at the limit as h approaches 0. So we'll have everything over h. Now, in order to simplify this, you might think about, well, could we combine some things here? And we can't really, because these are not like terms. They don't have the same thing under the root. You'll also notice if we try to plug in 0, we would just get root x minus root x, which would be 0 on top. We'd get 0 on the bottom. So we can't really do that here. This is a good case where we might want to multiply by the conjugate, I think. If you remember some of our examples in our video that talk about ways to simplify things algebraically to get a limit. So what we'll go ahead and do is think of this as root x plus h minus root x all over h. And so from here, we'll go ahead and multiply by the conjugate of this numerator here. Remember, the conjugate is just the same terms, but with the opposite operation in between. So we'll have plus between these two roots. And then we'll do the same thing on the bottom. We'll multiply by this. Remember, we need to multiply the same thing on the top and the bottom. Okay, so we go ahead and do some distributing now. I'm going to move down here. And we'll say the limit as h approaches 0. When we distribute the first roots into each other, we just get x plus h. The root will go away. And then if I do the outside and the inside terms, remember when I have conjugates, those should add to 0. So I get a plus root x times root x plus h, and then I get a minus root x times root x plus h. So those will add up to 0. So it's really just the last terms. So negative root x times root x is just going to give us x there. And then on the bottom, I'm going to go ahead and leave this. So I have h, and then I have this conjugate that I multiplied by, and you'll see why I leave this on the bottom here in a second if you don't already see it now. So notice what happens in the numerator, right? We have limit as h approaches 0. X plus h minus x just gives us h on top. And so then when we look at the bottom, we can see we're going to get some reducing of our factor h, right? So I can reduce this h with this h. Those both become a 1. And so we get the limit as h approaches 0 of 1 over that conjugate that we multiplied by originally, right? Root x plus h plus root x. Now what happens as h approaches 0? We get something that's nice. It's not 0 over 0 like we had before. I will just have a 1 on the top, but then when I plug in 0 for h here, I would just get root x for this one. So I'd get a root x here. I'd have another root x there. So on the bottom, I would really have 2 root x's, right? So we would actually have 1 over 2 square root x as our derivative for our original function, square root x. Let's look at another one that is a fraction here. So we have f of x equals 1 over x. If we go ahead and write down all of our definition stuff, so our derivative f prime of x is going to equal the limit as h approaches 0 of f of x plus h, means I need to plug in x plus h where my x is, right? So I actually get 1 over x plus h minus, so we've done that part, minus f of x is just the original, right? So minus 1 over x. So we've taken care of that. And then everything is going to be over h, right? So we have all of that over h. And if you remember doing some of these limits where we have fractions and fractions, complex fractions, a good thing to do would be to get a common denominator with this one. So what we can go ahead and do is multiply in x to the top and bottom here, and multiply in x plus h to the top and the bottom here. And then our numerator will at least have a common denominator, and then we can do some simplifying. So if we do that, our first expression on the top becomes x over x times x plus h. I have minus, and then our second expression here, I get 1 times x plus h is x plus h in the top. And in the bottom, I get that same denominator, x times x plus h. Right, so we'll have the limit of that all over h as h approaches 0. So now let's combine on the top. So we'll go ahead and continue down here. So we'll have the limit as h approaches 0. And now if I do x, be careful, distribute this minus, right? So x minus h. So we actually get x minus x would be 0. So we'll just end up with a negative h on the top. So we'll have negative h over x times x plus h. That's our numerator, fully simplified there, and then still over h on the bottom. And I think you can see what happens here, right? So think about maybe instead of divide by h, you bump up and multiply by the reciprocal. So here now, if we just think about this and we reduce the h's both to 1, then we'll end up with the limit as h approaches 0 of, we just get -1 on the top, and on the bottom I just have x times x plus h. Now, what is going to happen on the bottom as h approaches 0? Well, we would just get x in the parentheses, so we would get -1 over x times x, and that gives us -1 over x squared for an answer for this derivative. Let's do just one more example here. We'll do one that's a bit more fun at the end. Watch out when math people say fun, right? Use the limit definition to find the derivative of f of x equals x squared plus x plus 1. And so we'll go ahead and say f prime of x is going to equal the limit as h approaches 0. Now I have a couple of terms to plug in x plus h to, right? So f of x plus h will be, plugging in x plus h everywhere there's an x, x plus h squared plus x plus h plus 1, right? So that is just our f of x plus h minus f of x, so minus the original, minus x squared plus x plus 1. You can see I put these in brackets because we need to do a bit of being careful with distributing our minus, right? With when we have these. Okay, all of that will be over h. I'm going to go ahead and move to my next line here. So that's going to be the limit as h approaches 0. And I need to do some distributing here. Let me just do some stuff here in the first part. So think about x plus h times x plus h. If you need to write out two copies next to one another to see what this would be in order to do the distribute, then you could certainly do that. But we will get x squared plus 2hx plus h squared, so that's just this piece here, plus x plus h, and then also plus 1. So that is everything just distributed out. I'm going to go ahead and distribute my minus here just to make it easier. So we'll say minus x squared minus x minus 1. That is our numerator, and then all of that is going to be over h. And I'm going to scroll down, give myself some more room here. So let's go ahead and see if we can do any identifying of some simplification. We have an x squared here and a minus x squared, so those will add up to 0, right? You'll notice we also have a plus x and we have a minus x, so those will reduce to 0 as well. And we have a plus 1 and we have a minus 1, so those will reduce to 0 as well. So we have 2hx plus h squared plus h, all of that stuff, and then over h. So let's write that down. So we have 2hx plus h squared plus h. And then all of that is going to be over h. Now let's do some reducing, right? You'll notice everything in the top has a factor of h. Let's go ahead and factor out that common factor. That's going to reduce the bottom h nicely for us, right? So if I pull out an h on the top, then I'll be left with 2x in the first term. I'll still have an h left over in the second term, and then I will have a plus 1 for the last term if I factor out h. And that h that we factored out is going to reduce with the h on the bottom, and both of those will become a 1. So we will get then the limit. Let's clean it up just a little bit before we say the end here. There's no more denominator really, so we don't need to write a fraction. We have the limit as h approaches 0 of 2x plus h plus 1, right? And if you look at these three terms, h is really only in this second term. So what is going to happen as h approaches 0? Well, this term will disappear, right? And we will just end up with an expression of 2x plus 1 for our derivative of x squared plus x plus 1. All right, hopefully these few examples of working out a derivative using the limit definition will help you out when you need to do these. Thanks for watching, everybody. We'll see you in the next video.